Hello and welcome to another video. I'm Alex, and this week we're going to be looking at exponentials and logarithms, which will tie into the Edexcel Module C2, and this is going to be chapter 3. So let's jump straight in with exponentials. We are going to have to familiarize ourselves with the function of an exponential and the form of the graph that we can draw from it. So the shape of the graph is going to be really important. We need to be able to sketch different exponential graphs. So we're going to look at a couple of examples. First, let's look at the general form of an exponential, which is something like y equals a to the power of x. Now in this, a is any constant, could be 2, 3, 4, whatever. X is a variable. So basically an exponential is something where you have a power of a variable, and we'll see that will result in growth exponentially. As I said, we need to be able to sketch the graph for this, so we're going to look at an example. So we're going to start by looking at the example of y equals 2 to the power of x. And we're going to sketch this graph. I'm going to do that by just plotting a few values. So we're going to say x and y. We're going to go from -3 up to 3. So when x is -3, y is 1 over 8, 1 over 4, 1 over 2, 1, 2, 4, 8. Great. Okay, so now we can have a go at plotting our graph. So we're going to plot x against y, and we'll note that it goes to the point 0, 1, so we can mark that on there. Well, what does it do? Well, it's getting, as we go negative x, it's getting closer and closer to the x-axis, and as we're going positive x, it's getting further and further away. So it looks something like that. Okay, so that is the graph for a equaling 1. I'm just going to grab this because I'm going to need it in a minute. Oh, that's not worked. Okay, so let's look at another example. We need to note a couple things. First, that all of these graphs will pass through the point 0, 1 for a being greater than 0. Okay, they will all do that. If a is less than 0, then it's another story, but we're going to be looking at a greater than 0, and they're all going to pass through that point there. So let's take a look at something now. Let's say a equals 4. So now y equals 4 to the power of x. So again, if we get some values for x and y, now we have that we'll have 1 over 64, 1 over 8, 16 even. 1 over 4, 1 again, 4, 16, 64. Okay, so what's the difference from last time? Well, all that's changed is when we're at negative values, it's even closer to the x-axis. When it's at positive values, it's even further away. So that's going to look something like that. And it's going to grow even more, even quicker. So that's a equals 4. Okay, so, and similarly, if I picked a equals 1, so a number less than 2 this time, it would have been shallower and would have looked something like that. That should be a 2, sorry. A equals 1. Okay, so what do we need to know? We need to know that they asymptotically approach the x-axis as we go to negative infinity. And what does that mean? It means it gets closer and closer and closer, but doesn't touch it ever. Technically, it touches it at infinity. That's what asymptotically means, and it exponentially grows in positive x. Okay, great. So that's a couple of examples. What about another example? Those are all for a being greater than 1. Let's now look at what would happen if a is equal, say, a half. So a is now less than 1, but still greater than 0. So we'd have a equals a half, so y would equal half to the power of x. Okay, well, we're going to be able to really easily see what happens here, because we can say that y equals a half to the power of x, but we can write a half as 2 to the power of minus 1. Okay, and that means that using power laws we can write this as 2 to the power of minus x. Okay, so all that we've done is we've replaced x with minus x. So now every value that we had of y that we had for x, we now have for minus x. So what does that look like? Well, it looks like a reflection in the y-axis. So it will still go through this point 1 here, but instead of going up like that, it now goes up like that, or it goes down like that. That's a equals a half. So you see, if we've got a number that's bigger than 0 but less than 1, it looks exactly like it does for bigger than 1, but it's reflected in the y-axis. Okay, brilliant. That's all we need to really know about exponentials for now. We just need to be able to sketch the graphs. So we're going to move on to logarithms, which are obviously very, very closely connected to exponentials. So we're going to take a look at them. We're going to define what a logarithm is. And to do that, I'm going to write this statement to begin with. I'm going to write that a to the power of x is equal to n. Okay? Now, our logarithm is defined as this, and this is the way that we write it. We write that log n base a, so this little a here is called the base, and we write it smaller and lower, would be equal to x. Okay, and what this means, what this logarithm means here is, if you were to put this into a calculator or whatever, it's what power do I need to raise a to get n? Okay, I'll say that again. What power do I need to raise x to get n? Okay, so above we had that a to the power of x was equal to n. So we need to raise a to the power of x to get n. So that's what a logarithm is defined as. Okay, I know that might be slightly confusing with abstract numbers, so I'll do a little example. If I wrote log 16 base 2 is equal to 4, that would be a true statement. And why is that true? Well, our logarithm means what do we need to raise 2 to get 16? And we need to raise 2 to the power of 4. So another way you could write this is 2 to the power of 4 is equal to 16. Brilliant. That's what a logarithm is. At this point, we're going to note a couple of things about logs that will be really useful for solving problems throughout all of your maths. And that's two things. The first one is this, that log 1 base anything, so any base, is equal to 0. Why is that? Well, it's because it implies that a to the power of 0 is equal to 1 if a bigger than 0. Okay. The next one is that log anything when its base is the same, so log a, base a, is equal to 1. Why is that? It's because it implies that a to the power of 1 is equal to a, which we know is true. Great. So those are two things that are really important for us to know about logs. The next thing that we need to be able to do with logs, or the first thing even that we need to be able to do with logs, is solve simple equations with an unknown. And the first thing that we'll do is solve them when the log is to base 10. And the reason we'll do that is that on your calculator, there will be a log button. There'll be two. There'll be one that's log, and there'll be one that's ln. We'll talk about ln another time, but for now we're going to do log, and it will be to the base 10 on your calculator. And it's important to realize that in a lot of questions, it may not tell you what the base is. And if it doesn't tell you what the base is, so it may be written just like this. It may be written like log 30. Okay? And if it doesn't tell you the base like this, and it's written like this, it's a safe bet that it's going to be to the base 10. Okay? But you should always read the question to make sure that they've not told you otherwise. Okay? So we need to be able to solve equations like this. 10 to the power of x is equal to 250. The way that we're going to solve that is by using our definition of what a log is. Now, our definition of a log was, what do we need to raise the base to the power of to get the argument in the log? In this case, what do we need to raise 10 to the power of to get 250? And the answer is x. Okay, as you can see, we need to raise 10 to the power of x to get 250. And then all we have to do is put that into our calculator, and we would get that x is equal to 2.3979, I don't care about the rest. Okay? Take a moment just now to have a go. So get your calculator out, find the log button, put log of 250, and make sure you get the same answer. Okay, good. Hopefully you've given that a try, and you got the same answer as me, as long as I did it right. Okay, so that's the first thing that we need to be able to do with logs. Solve simple equations like that. The second thing is that we need to know about log laws, okay? There are several logarithm laws, 3 to be precise, and we need to know what they are, and we need to know how we're going to use them, okay? How we're going to use them will become apparent a lot more through doing questions. Yeah, we're going to look at where the laws of logarithms come from, and hopefully that will help us to understand them and be able to use them. The first one is called the multiplication law. And where we're going is that log base anything x times y is equal to log x add log y. That's the multiplication law. Now let's have a look where it comes from. The way that we're going to do this is we're going to set something up. So we're going to say, we're going to let x equal a to the power of b. Okay? Now because of our definition of a log, we can also write this statement as log base a of x is equal to b. Then we're also going to define y as equaling a to the power of c, which means that we can write log a base a y is equal to c. And what we're going to do now is we're going to multiply x and y together. So we're going to say that xy is equal to a to the power of b times a to the power of c, which using power laws is equal to a to the power of b add c. Okay? Now what we're going to do is we're going to add the two logs together. So we're going to have that log of x add log of y is equal to b add c. And I'm going to call that 1. Okay? Now what I'm going to do is I'm going to rewrite xy equaling a to the power of b add c using our definition of a log again. And this time we'll have that log of a, log base a xy is equal to b add c. I'm going to call that 2. Now we can see that we can equate 1 and 2. And we'll see that log of xy is equal to log x add log y. That's the multiplication law. Okay, it's important to note that I've written that very poorly. It's important to note that they have to be the same base, okay? So the multiplication law and all of these laws only work when you've got the same base, okay? The next law, I'm not going to derive because it comes from the exact same place as the multiplication law, and it's the division law. Okay, and all you do this time is divide instead of multiply, and you get that log x over y, and I'm not going to write the base in now because we don't need it, because we know that it's all the same base, is equal to log of x minus log of y. Okay? That's the division law. Comes from the exact same place. Sorry, I've written that wrong there. There should be an x. It comes from the exact same place as the multiplication law. And again, we note that they need to all be the same base. Okay? Brilliant. We've got one more law, which is the power law. And the power law says this. What we're aiming for is that log of x to the power of n, okay, and it's log of that whole thing is equal to n times log of x. Okay, that's where we're heading. So how do we get there? Well, the first thing we're going to do is we're going to say let this thing that I'm going to call m equal log of x. Okay? Now from that, we can say that x, base a, x is equal to a to the power of m. Okay? Now what we're going to do is we're going to raise x to the power of n. And we'll get a to the power of m all to the power of n. Which again, using our power laws, it's all about power laws in this, x to the n is equal to a m n, okay, which means that we can write log base a x to the power of n. This is using our definition of a log. So what do we need to raise a to the power of to get xn? Well, that's equal to m times n. Now if we substitute our definition of m back in, we get that log base ax to the n is equal to n times log of x, which is the power law. Okay, those are our three laws that we need to know. And it's really important that we can use them. So we need to be able to use them in simple ways to do calculations to make our life a lot easier. For example, let's do the example of simplifying log base 3 of 10 add log base 3 of 6. I'll give you a moment to give that a try in your head, maybe. It's going to be the multiplication law, and we can say that this is the same as log base 3 of 60. Okay? Similarly, what would log base 2 of 10 minus log base 2 of 2 be? Well, it would be log base 2 of 5 using the division law. And then one more, what would log base 10 of 3 squared be able to simplify to? Well, it would be the same as 2 log base 10 of 3 using the the power law, sorry. Okay, so those are our three logarithm laws, and they're really important for us to be able to use them. We need to be able to use them to answer questions where we might not have something, say, to the base 10 like we had before. We might have something else. So we need to be able to use it to solve things like 4 to the power of x is equal to 15. Okay, how are we going to solve this? What we're going to do is we're going to do something which we call taking logs of both sides. Okay, so we take logs of both sides and we end up with log, I'm going to use base 10, 4 to the x is equal to log base 10 of 15. The reason I use base 10 is, as I said, it's the log that's on our calculator, so it makes doing the calculations a lot easier. We don't have log base 4 on our calculator, so it becomes a lot harder. Okay? Well, how are we going to work this out? Well, using the power law, we can rewrite this left-hand side as x times log base 10 of 4, and it's still all equal to log base 10 of 15. Then we can divide both sides by log of 4, and we get that x would be equal to log base 10 of 15 over log base 10 of 4. And we can put that in our calculator, and we'd get that x is equal to about 1.95. Okay, so we need to be able to use them in context like that to be able to go from things that we can't answer, like what's log of base 10 of 4 to the power of x, to things that we can. We can put log of base 10 of 4 in our calculator. Okay, moving on. The next thing that we need to be able to do is we need to be able to use the change of base law. So sometimes we'll have questions where we've got logarithms of different bases, and we need to be able to change the base so that we can answer the question. Okay, the change of base law says this. It says that log base a of x is equal to log base b of x divided by log base b of a. That is our change of base law. Let's have a look where it comes from. Okay, what we're going to do is, again, I'm going to say let m equal log base a of x, which again means that a to the power of m is equal to x. Now I'm going to take logs of both sides here. Okay, I'm going to say take logs of the left-hand side and the right-hand side, but I'm going to use log base b. So we get the log base b of a to the power of m is equal to log base b of x. And we want to use our power law on this left-hand side, and it becomes m times log base b of a is equal to log base b of x. We divide both sides by log base b of a. We get that m is equal to log base b of x divided by log base b of a. And then all we have to do is substitute in our original definition of m, and we get that log base a of x is equal to log base b of x divided by log base b of a. Change of base. Okay, we need to be able to use that. For example, let's look at solving for x. This is quite a complicated one, okay? So bear with me. This is a complicated example that's going to use a few different things. We are given that we need to find the value of x that satisfies log base 5 of x, add 6 log base x of 5 equals 5. Okay? The first thing that we notice is that we've got logs, but they're different bases, which before would have been a big problem for us, but we now have our change of base law. And so what we're going to do is I'm going to change the log of x, log of 5 base x to something with base 5. Okay, so log base x of 5 becomes log base 5 of 5 over log base 5 of x. But if you remember from earlier on, if we have log of something and the same base, that's just 1. So that becomes 1 over log base 5 of x. So we can substitute that back in to 1, and we get that log base 5 of x add 6 over log base 5 of x is equal to 5. And what I'm going to say is let y equal log base 5 of x. And that's going to allow me to write this as y add 6 over y equals 5, which multiplying by y becomes y squared add 6 equals 5y, which is y squared minus 5y add 6 is equal to 0, which we can factorize to y minus 3, y minus 2 is equal to 0. So y equals 3 or y equals 2. Then we need to go back and we need to realize that we said that actually y was equal to log base 5 of x. Okay, but we can now write that in two different ways. We can say that log base 5 of x is equal to 3, and log of base 5 of x is equal to 2. And what did our definition of a log, what was our definition of a log? Okay, it was, the answer is, what do we need to raise 5 to the power of to get x? So x just becomes 5 to the power of 3 here, and it becomes 5 to the power of 2 here. So x equals 125, and x equals 25. And there we go. That's how we solve questions like that. Okay, that's all we're going to look at today. Hopefully, I know there's a lot of content there, but hopefully you can watch through at your own pace till you understand it, and you can find some questions to try to test yourself out. Okay, thanks for watching, and I'll see you again next time.